Swayam. Digital India. Educated India.
However, there is another notion of complexity, which is the notion of what is called a strong. Okay, so strong running time bounds are ones which don't actually depend on the size of the representation. Okay, if you're willing to assume that you can do what is called infinite precision arithmetic, okay, which means you give me square root of 2 and e to the pi, right, as two operands. I can add, subtract, multiply, divide them in order one time, right? Exactly, let us say. Okay, it's a theoretical model, it's not done in practice, but there is cost 1, right? One arithmetic operation for even like infinitely large operands, right? So under this model, the question is, how much time will you take to compute an answer for your given problem, right? So in such a case, right, value iteration, by the way, will still be having this dependence on the size of your representation, right? Because it's something that it needs in order to terminate. And likewise, interior point method, ellipsoid method will also have this dependence. However, there are approaches that can give you bounds that don't depend on the size of the representation. They depend only on the number of states and actions in the MDP, right? Or number of constraints and variables in the linear program. So this was one of the early results in the context of linear programming, right? Which showed that it actually suffices to do a sub-exponential number of arithmetic operations in order to solve a linear program, right? So when we take our MDP and apply it through the linear programming route, right, it's possible to show that there is a randomized algorithm that in expectation, it will take polynomial in n and k times this term here, right, this factor here is e to the square root n, right, up to whatever order complex, e to the c times square root n, let us say, right? So anything that is e to the little o of n, right, that's called a sub-exponential bound. Okay, it's not exponential because there's a square root over here. Even if this was n to the 0.9, right, this would be a sub-exponential bound. So the thing about this is that this is a strong bound. Okay, it has no dependence on the number of bits that you're using to represent. Okay, even if you make that larger and larger and larger, this bound will stay the same, assuming, of course, you're doing infinite precision arithmetic. Okay, so strong bounds are quite popular. They have a sort of fundamental appeal to theoreticians, right? Because they look at only the most fundamental quantities describing the problem. In our case, the number of states and actions. Okay, so policy iteration, it turns out, you can show both non-strong bounds. So policy iteration is known to do at least as well as value iteration in terms of the number of iterations. But it can also support strong bounds, right? So we know that every policy evaluation, right, the step that happens in every step of policy iteration is a polynomial time step, right? And the number of steps that policy iteration performs, right, is also something that is at most k to the n, right? So policy iteration is almost like set up to provide strong bounds, right? So the question is, how tight, right, can we make the upper bounds for policy iteration, right? One thing to mention is that policy iteration still has not been shown to have sub-exponential bounds. Okay, the tightest strong bounds, strong upper bounds for policy iteration are still exponential in the number of it's something to the n. Okay, n is being the number of states. It's not something to the square root of n or any other like little o of n function. Okay. However, my own research in the last few years has precisely looked at improving the strong upper bounds for policy iteration. Okay, we have bounds that are better than the trivial bound of k to the n. They're also better than some of the advances that were made on top of k to the n. Okay, so that's what I'm going to present to you in the next few slides. So this is the literature, let's say towards the end of the by 2000, right? These are results from 1960s and 1999. So Mansoor and Singh, okay, in their 1999 paper showed for Howard's policy iteration, okay. Remember, this is the greedy switching rule, that if you apply it on an MDP that has only two actions, right? The number of iterations you will perform is a linear improvement over 2 to the n. Okay, 2 to the n is like a trivial bound, right? You'll never visit every policy twice, so you can't visit more than 2 to the n policies. But they showed that you'll actually do a little bit better, right? You won't visit more than 2 to the n divided by n. And this sort of also translates to general k action MDPs when k can be greater than or equal to 2. The random policy iteration algorithm that they specified, right, does better. Okay, randomization does help. So in expectation, their random PI, right, or random policy iteration algorithm will take 1.71 something to the n iteration, and when you generalize to k, right, multiple actions, that becomes something like k over 2 to the n. Okay, it's k to the n divided by 2 to the n for large k. All right. Okay, so contrast this with existing lower bounds for policy iteration. Okay, so the main algorithm that has been analyzed from the lower bounding aspect is Howard's policy iteration. Okay, to date, okay, the tightest lower bound for Howard's policy iteration on n state 2 action MDPs is linear in n. Okay, so there's a paper from 10 years back that shows that you'll take at least, I think, 2 times n iterations on certain MDPs if you do Howard's policy iteration. The upper bound is 2 to the n divided by n, and the lower bound is omega of n. Okay, there do exist genuine exponential lower bounds for other types of policy iteration. Okay, so one of the switching rules that we mentioned was simple policy iteration, right, where you're only switching the rightmost state. So a 94 paper shows that that strategy can actually visit every policy in an MDP. Okay, so an MDP with n states and 2 actions, by construction, right, it is shown that you will visit all 2 to the n policies. So in terms of upper bounds, right, there are some improvements over the trivial bound of 2 to the n, right? For Howard's policy iteration, that's only linear. It is exponential when you do random policy iteration. In terms of lower bounds, there is a genuine exponential lower bound for simple policy iteration, but not for Howard's policy iteration. Okay, in fact, not for Mansoor and Singh's random PI either. Okay, so this is what we inherited. In the last 5-6 years, we've chipped away a little bit at these results and made, I would say, very, very small amount of progress. So in terms of giving credit, right, I want to emphasize that many of the papers that I'm going to list right now are ones I have co-authored with students, okay, who have all taken previous offerings of CS747. Okay, so yeah, if I'm giving the name of the student, I'm also underlining it. All right, so let us look at results in 2 separate categories. One is for 2 action MDPs, and the other is for general K. So remember, the main effect of k equal to 2 on policy iteration is that when you say you want to improve a particular state, right, and the MDP itself has only 2 actions, there's no choice in which action you will improve to, right? There's only one improving action, you have to pick it. When you have more than one improving action, there is that choice, right? And this is partly the reason that k equal to 2 is a little bit easier to analyze than general K. You'll usually find better bounds for k equal to 2 than you do for k greater than or equal to 3. Okay, that's also something that we find in our results. So, but what are the results themselves? Okay, so with Utkarsh Mal and Ritesh Goyal, okay, we devised an algorithm called batch switching policy iteration. So this is a deterministic algorithm. Okay, and for this we were able to show an upper bound of 1.64 something to the n iterations. Okay, so notice that the baselines that we have are 2 to the n divided by n for Howard and 1.71 something to the n for Mansoor and Singh's random policy iteration. So we actually have a deterministic policy iteration algorithm that does better than both of those, okay, on 2 action MDPs. If we allow for randomization, right, we are actually able to do better than 1.6479. We bring this down to 1.6001 to the n iterations. So this can actually go down even further. Okay, we've not published, but this is work along with Meet Taravia, okay, from paper that we published only last year. Okay, and remember, when I'm giving bounds for random variance, it's the expected number of iterations. Okay, so when you say something is an upper bound for policy iteration, right, what you mean is that for every end state 2 action MDP, for every starting policy, I'm guaranteeing that the number of iterations you will take is, in one case, 1.6479 to the n iterations or fewer, the other, in expectation, 1.6001 and to the n iterations or fewer. Okay, so there's a worst case over all MDPs from that family and all starting policies. We also have some results for k greater than or equal to 2 for general k. So with Anchit Gupta, 2-3 years back, we generalized batch switching policy iteration to work with more than 2 actions. And the resulting bound we have is k to the 0.7207n, which is better than k to the n over n, right, exponentially. Thereafter, we also have improved this bound to k to the 0.7019n. Okay, this is again a deterministic algorithm. This is work with Meet Taravia. If you're allowed to randomize, right, you can actually do better than poly k to the n. So both of these bounds are polynomial in k raised to the n, right? So we've shown that you can actually do order log k to the n by doing like actually a simple generalization of one of the algorithms you've seen, right? So you saw simple policy iteration. So basically, we've shown that in simple policy iteration, if you additionally pick your improving action uniformly at random, right, then it will take you at most 2 plus log k minus 1 raised to the n iterations. Okay, so part of my giving you these pointers, right, is that I actually believe you'll be able to follow these papers and understand the results. Okay, the fact that it is research, I hope, does not put you off, and it sort of seems like something that is very remote from what you're studying here in class, right? You've actually done all the basics to be able to appreciate the algorithms that I'm not giving you the entire algorithm here, but just discussing the result. So some interesting work with Meets Taravia also resulted in some analysis of Howard's policy iteration itself. Okay, so imagine Howard's policy iteration on multi-action MDPs. So often you're going to be encountering improvable states that have multiple improving actions, right? So imagine doing Howard in the sense that every improvable state you will improve, but if you have choice, you will determine that uniformly at random. Okay, you will pick an arbitrary, you will pick an improving action picked uniformly at random amongst the options that are available to you. So if you do that, then we've shown some analysis establishing that Howard's policy iteration will take at most square root of k log k raised to the n iterations. Okay, so that's a fairly big improvement from k to the n over n. Okay, unfortunately, this does not translate into a similar tighter analysis for 2 action MDPs. Okay, this bound doesn't really make sense when you do it with k equal to 2. Finally, okay, this is maybe the most recent. You can see that the year on this paper is 2020, right? It's the same year that you're doing this course. We have a lower bound, okay? So with Ashutosh, Consul, Dedia, Kirwadkar, and Shah, okay? We have shown that there exists an MDP and there exists a starting policy and a particular form of policy iteration, okay, which will take square root of k to the n iterations to reach the optimal policy. Okay, so there exists a member of the PI family that takes an exponential number of steps to complete on k action MDPs. So if you remember, right, for k equal to 2, we actually have a result showing that there is a variant of PI that visits all 2 to the n policies, all the policies, right? So here we've not been able to show a variant that visits all k to the n policies, but we've shown like square root of k to the n policies. Okay, so it's still an exponential lower bound, but it's not k to the n. All right, good. So at the end of this, right, based on sort of my own understanding of policy iteration and the analysis, there's a number of unresolved questions. Okay, so you probably won't be able to appreciate where these things are coming from right now, but I mean, just take it from me that they kind of arise naturally from the analysis that has gone into the papers that I showed you. Okay, So let me just list these out. If you're interested, I'm happy to talk more. Okay. So we are fairly convinced. I am fairly convinced. Okay, I am willing to conjecture that Howard's policy iteration on two action MDPs should not take more than 1.61 something to the n iterations to finish. Right, the bound we have right now is 2 to the n divided by n. That has not been breached yet. Okay, but there is enough indication that the bound must be tighter, and we basically believe that at the very least it should be upper bounded by the Fibonacci sequence, right? So Fibonacci numbers are basically like 1.61 golden ratio raised to the n. So we believe that that's a bound on upper bound on the number of iterations Howard should take on two action MDPs. It's not been shown. Okay, it's a problem that has not yielded much progress so far. Again, right, Howard's policy iteration, by all counts, right, if you actually implement this and see, you will find that Howard's is almost always preferable to any other variant of policy iteration. All right, although the results that we have are not saying that, right? So we have batch switching policy iteration, for which we have shown an upper bound of 1.64 something to the n. If you run that version of batch switching policy iteration, comparing with Howard on a typical MDP that you encounter, you'll find Howard doing much, much, much better, right? There's no proof. So one question is, amongst all deterministic policy iteration algorithms, right, is Howard actually the most efficient, right? If such a claim is proven, right, then it will follow that the bound that we've shown for batch switching policy iteration also holds for Howard. But again, right, this is a hope or a conjecture or a claim. It's not really a proof yet. Okay, it's not a proven result. In terms of lower bounds, can we do better than the linear lower bound for Howard? Right? Are there two action MDPs on which Howard takes more than n steps? Right? Does it take n log n or n squared steps? Anything that is higher than n steps? Somewhat different question. Okay, is looking at Howard's policy iteration on a special class of MDPs. So imagine MDPs in which the transitions are all deterministic, which means when you take an action from a state, there is a fixed next state. Okay, there's no stochasticity in the actions for any action. So such an MDP is called a deterministic MDP. There are algorithms, including certain policy iteration algorithms, that have been shown to be strongly polynomial on such MDPs, on deterministic MDPs. In other words, on such MDPs, the number of operations that they'll perform will be polynomial in n and k. We might believe that Howard is also strongly polynomial on such MDPs. There's no proof. Okay, so that is again something that is open. I already sort of mentioned this in passing, right? We've shown a lower bound of square root of k to the n for general n state k action MDPs. Can we show a lower bound of k to the n itself, right? A policy iteration algorithm that visits all the policies in a k action MDPs, again open for k greater than or equal to 3. Finally, okay, so this is zooming out quite a bit. If we take MDP planning as a problem, right? Question is there any algorithm that can give us a strongly polynomial bound for MDP planning, right? Which means given an n-state k-action MDP, the number of arithmetic operations you'll perform to give the optimal policy is polynomial in n and k. See, the best bounds we have right now are ones coming through that linear programming route. They are sub-exponential. They're like e to the square root of n, right? They're not exponential, but they're not polynomial yet, right? Polynomial is smaller than sub-exponential of that form. So this question is open, right? And it's interesting. This question is also open, by the way, for linear programming itself. Okay, but MDPs clearly are a simpler problem than linear programming, right? They're not as general, and so it remains unanswered also for MDPs. Okay, so this is all food for thought. Again, this section on the more recent work, optional. It's up to you whether you want to look at it in more detail. All right. So let us now summarize. And what we are summarizing now is not just this week's lecture, but our entire discussion on MDPs, okay, as a part of the course, which is weeks 4, 5, and 6. So what are MDPs? MDPs are a way of mathematically formulating the problem of sequential decision making. Right? When you have an action, it has stochastic transitions to states from which, again, you have to take actions. You want to maximize expected long-term reward, right? So this generic formulation has a large number of applications. We saw some in the week 4 lecture. There are also minor variations around this, okay, in terms of defining what you want to optimize, right, how you define rewards, etc. But regardless, right, the basic element, right, that underlies an MDP, right, is the idea that you can associate an MDP with optimal behavior, okay, which is represented as an optimal policy. So the problem of finding an optimal policy for a given MDP, that is the MDP planning problem. So as a part of this course, we have seen 3 large families of such algorithms: value iteration, policy iteration, and linear programming. So they have their pluses and minuses. Okay, so in practice, I wouldn't say that one of them is uniformly better than the others. Okay, so depending on the problem instance and the sort of attributes that the problem has, maybe value iteration will do better, or linear programming, or policy iteration. But in practice, on relatively small MDPs, you should take that any one of them will do very well. Okay, so you will actually maybe implement, when you implement this, right, you will sort of see for yourself that if you're given an MDP with, I don't know, 1,000 states and 50 actions, right, whatever transition probabilities you have, unless somebody really takes a lot of pain, right, in constructing a difficult instance for you, any of these methods will do lightning fast. Okay, so that's one good thing. And although we have described these as 3 separate families of methods, there are some approaches that combine them. Okay, so there is a family of algorithms called asynchronous dynamic programming, okay, ADP, which are basically a combination of value iteration and policy iteration, okay, with sort of different degrees of doing one or the other. So yeah, I mean, it's if you want, you can sort of look up. I think Sutton and Bartow does mention asynchronous dynamic programming, but yeah, I think you have enough understanding of the individual algorithms, right, to be able to appreciate any combinations thereof. We actually did this fairly theoretically as a part of the course, right? For each of these families of algorithms, we formally showed correctness. Okay, we did it from the ground up. We used maybe a couple of results, right? Things like Banach's fixed point theorem, contraction mappings, where I told you this is just known from the literature, but thereafter we put together all the proofs completely. Okay, so it will help you to have that sort of familiarity with the mathematics underpinning these algorithms, right? The proofs of correctness. One of the other things that we did use was the Bellman optimality operator and the Bellman operator. Okay, so these are both concepts that I think it's good for you to know. When we go from here, right, to the next step, we will continue to use these quite frequently. But what really is the next step? The next step is going from planning to learning. Okay, so technically planning is the problem that we solve when we are given the MDP in full, right? We are given, these are the states actions, this is the transition probability matrix, these are the rewards, this is the discount factor. But very often in practice, right, you are not given, let's say, the transition probabilities as a table. Rather, the agent is allowed to take an action from a state and see where. So it's interacting with an MDP where the next state will actually be drawn according to the transition probability function, but the agent just gets to see the next state. It does not get to see the underlying probability with which the next state was generated. So if the agent has to interact with an MDP like this, right, the question is, can it still learn enough about the MDP optimal actions, right? Over interaction, it slowly puts bits and pieces of what it has seen together, right, and says, well, probably this is the MDP that I'm interacting with. This must be optimal behavior. Can it converge to optimal behavior in the limit, right? If we solve that problem, right, the problem we are solving is what is called the reinforcement learning problem. Okay, and in order to do this, also needs to typically do a good balancing of explore and exploit. Sometimes it should take promising actions. Sometimes it should just explore, right? Take an action that it does not know so much about. So literally the coming together of bandits, which we did in the first 3 weeks, and MDPs, which we've done in the next 3 weeks, will come together in what is to follow, and that is reinforcement learning. We will do reinforcement learning. everything that you have done up to date is going to come handy. Okay, that will really be the basics on which we build week 7 onwards. Okay, so we're done. Stay safe. Have a happy week ahead of you, and I'll see you in week 7. Bye.